start off. So beta elimination reaction, the reaction in which, okay, whatever, this part is fine. Now, this is very wrong. Never write your reaction like this. Your synopsis absolutely should not be this. This is wrong. And in this particular case here, what does this basically mean here? What is it supposed to be?
So when the solvent is weak base, then
Okay, weak base.
like,
Okay.
oh, you don't understand.
I understand what that meant. Weak
Oh
base.
yeah, I got it. Yeah.
So he has discussed E1 here basically, right?
Yeah.
Okay, I'm not doing this fellow's discussion of E1. Okay. So let's start off. So if I'm going to be having elimination first order, what does elimination first order really mean? What is it really competing with? So first of all, when you want to understand the elimination reactions here, the key thing which you need to pick up on here is this. You are having many parts in a reaction. All right. So what do I mean by many parts in a reaction? Let's say I'm having the same substance which you guys have taken. Okay, this was the compound which has been taken over here, correct? So this compound here, if I'm going to be considering it, now a better system to consider and start learning elimination is this guy. So I'll be starting from here. I'm not going to be starting from the chlorine one. The chlorine one will come to when we come to it, because this is a better example to understand the game here. So what I'm going to be using is, I'm going to be actually using concentrated sulfuric acid. You have done this mechanism, yes?
Yes.
So what is the mech for this guy?
Give me a second.
So
it dissociates into ions first.
Which
H
one
plus
dissociates
plus.
into ions first?
The concentrated H2SO4 or H3PO4. Then that H plus will come and attack the OH minus. The OH.
Good. So you have
Positive
good
charge
clarity as to what's happening here. So explain step by step here as you're continuing. H plus comes and attacks here.
H plus comes
next?
and bonds with OH. Then you get a OH2 plus.
OH2 plus. Okay.
Then we remove. Wait 1 second. We remove the water molecule.
Good. We remove the water molecule. So the water molecule takes the 2 electrons present here and gets out. Okay.
So it takes the 2 electrons because it's more electronegative, right?
Yes, exactly. The oxygen here is something which is having a positive charge, and it is of course far more electronegative. Whenever you are looking at electronegativity is the property which basically describes control of a particular atom in a bond over the bonded pair of electrons. So the more electronegative atom is always going to be the one which is going to be controlling the 2 electrons present in a bond pair. So yes, because the oxygen is more electronegative over here, it takes the 2 electrons and it gets out. So what will it become?
Carbocation is formed.
Carbocation is formed. Okay. And now is when things get interesting.
The negative part.
Okay. So here is where your teacher has not really given you proper information. So here, what is the pathways available right now?
The SO4, HSO3 minus could come and attack.
Okay. So he has discussed
Or
other possibilities then as well to an extent. Okay. So HSO3 minus can come and attack. Then what else can happen?
there is no watchman.
What else can happen? So the complication which happens here is mainly because of the fact that your teacher was very smart to take a case which basically does not ask so many questions. Mainly because most of the other possibilities get shut down the moment you take this big guy. This is a very bulky fellow. It is going to be offering only one pathway as a possibility. Organic chemistry is something which is goddamn like real life. It is real life. So there is never going to be one possibility ever. But in this case, you don't see more than that one possibility predominantly. So let's take the same thing with a slightly different example. I'm going to be considering ethanol now. If the same thing happens here, first we'll effectively end up having H plus produced, which will go attack this guy. This will end up becoming an OH2 plus 1, which then ends up kicking this guy out to release a carbocation, which is pretty much where we are. There were some paths available for us. First was, we basically said HSO3 minus can come and do business over here. Or we can have this guy getting out. This guy can shift over here. That will be our E1 pathway. Right?
Sir, when all does this, like, an atom is leave the group, like, when does that happen?
We'll talk. In this case, this has happened.
Okay. Oh, when's it conjugation?
Sorry?
Or something. Okay.
You're asking what exactly? Be more specific. Are you talking about the OH leaving or the hydrogen leaving?
Hydrogen leaving.
So, this guy is your pain center now?
Yes.
Correct. So, this carbon is going to be something which is going to be extremely electron deficient right now. It wants to reach octet however possible. So, on this other carbon atom here, what is going to be happening is this carbon is now positively charged. Now, it doesn't have octet. So when there is no octet, what happens to the size of that system?
It decreases.
Decreases dramatically here, correct?
Yeah.
It's far smaller in size. So the electronegativity of the atom is now far higher.
Greater. Yeah.
Far higher than what it used to be. So when it is far higher than what it used to be, what will simply happen here is this carbon atom, this fellow which is having a positive charge, will now literally do the same thing. You guys learnt about rearrangement of carbocations. Why does it happen?
Stability.
Why does it happen? Only on those ones specifically. And why specifically in that order?
In which order?
You learnt about some rearrangement. I mean, when the rearrangement is happening, this guy is better than that guy is better than this guy and shit, na? A priority order you would have been given.
I don't remember.
Knowing your teacher and the kind of stuff he's taught you, I'm quite sure he would have given you a priority order for rearrangement.
No, we didn't. Oh, yeah.
Yes.
Wait, I don't think this is. I don't think we had it. Hydrate shift only, right?
Hydrate shift is going to be better than methyl shift, obviously. He has not given you a full-fledged priority order there at that season.
Yeah, no.
I don't know what is going through this fellow's mind. He teaches like some shit at like ridiculous depth, some basic shit which are supposed to be given, he doesn't give. Okay, so yeah, hydride shift is better than methyl shift alone. You have learned so far then.
Yeah.
Okay, so let's quickly talk about why the shift happens. The shift happens based on the same reasons which I'm talking about here. This carbocation is something which is now far more electronegative. So it literally is like this. Let me show it to you straight away. This will be easier. So let's say I'm considering this as the molecule here. Let's say this is the carbon atom which is screwed over. All right. So if it's a carbon atom which gets screwed over, let me put it like this. Some planar phenomenon. Okay. So this is this carbon atom here becomes a carbocation. It's a planar fellow. So what happens here is this fellow has got 3 groups on it. So this carbon is now far more electronegative. Being far more electronegative, it doesn't care what it is targeting here. This carbon atom here will target any one bonded pair of electrons here. When I say target, think of it like this. This carbon is bonded to this. This is highly electronegative. This fucker is satisfied. All right. So this guy is jealous literally for the electrons present in these 3 bonds here. Literally. So effectively speaking, bluntly apply KQ1 Q2 by R squared. Whichever is going to be having more electron density present here and is closer to this will be pulled away by it.
So if there is a double bond there, then that pi bond would go away.
No, there will be no pi bond. The pi bond, fair enough. If you're having a pi bond away, pi bond.
Yeah, that's what I mean.
Yes, absolutely. Why? Because pi bond is weakly
more electronegative.
It is not that
more
tight
electron density
over here. So that will basically directly shift over there. That's the idea. Yeah. So literally speaking, this desperate creature will pull whatever is closest to it, whatever is maximum for it.
Sir, if it was deficient enough, would it take more than 1 bond?
No, it will never take more than 1 bond. Because the moment, remember, think for a second, if this is going there, remember everything is real time. As and when this guy is getting satiated, it will lose its electronegativity.
Oh, but then what if it had +2? And then
there will be never a +2. Don't make up theoretical bullshit which you are not going to be ever getting. There is enough complication in the world already with organic chemistry. Don't make up more unnecessary shit. Don't allow your brain to come up with your physics shit here. Okay, this has got enough complications as is. In this here, the basic idea here is this extremely jealous, highly electronegative thing will effectively literally pull these electron densities in any one of the bonds. The simple factor will be pure KQ1 Q2 by R square. You're familiar with what KQ1 Q2 by R square is supposed to be?
Yes, sir.
Pure electrostatics. So this pure electrostatics here will basically look at what factors, which factor will be most important than the factor over there. If I'm considering R. Beautiful. So now you understand why hydrogen goes.
Sir?
Why is hydrogen? I'll give you the priority order for the shifting here. That is, in this shifting here, there is going to be a priority order associated with it. The priority order will basically be hydrogen.
Like leaving group.
Don't call it leaving group. You're using some unnecessarily dangerous words here. Leaving group is something very important in organic chemistry. Literally, that's what I'm about to discuss right now.
Oh.
So don't call this one as leaving group. That is very, very dangerous. So priority order for shifting, let me quickly give it here. So effectively, you'll end up having hydrogen or hydride shift being the best. Then you will end up having any benzene ring with a plus R, then a plain benzene ring, then a benzene ring with a minus R. Then you will end up having a tertiary carbon. Then you'll have secondary carbon. Then you'll have primary carbon. And then you'll have methyl. Methyl is one of the worst things to shift. Now, why is it in this here like this? The reason is mainly because of what I just explained here. When you're going to be having this carbon here pulling a bond over here, it is purely dependent on KQ1 Q2 by R square. Now, when it comes to the Q1 and Q2, this bond over here or this bond here or this bond here, whichever bond has maximum electron density will have maximum Q. Which means it will have maximum attraction by this guy, which means it will pull it. That part explains your why benzene ring with plus R is going to be the best. Because if there is a benzene ring with plus R connected here, it will be feeding electron density here. That means this bond will be very highly electron rich here.
Will be, yes.
So think of it like this. This guy is a pickpocket. All right, who is going to go, who is, or not even a pickpocket. All right, let's say you say this is going to be very nasty, but it's a real example which can happen. So it's worth it to discuss. Let's say you've graduated out of college, you're jobless, but you're a bad character. Nobody's there around you, right? Nobody's around you, yes?
Yeah.
But you have got bad character. All right, you're still staying at your parents. You have bad habits. What will you do? You'll start lifting from your house.
Yeah.
Possibility will creep into your mind.
Yeah.
And when you're doing that, you'll take the lowest hanging fruit, correct?
Yeah.
You will not try going after unnecessarily risky stuff. But
Yeah.
you'll take whatever you can take easily, but high value. Because you don't want to do multiple times. That increases the probability of getting caught.
Yeah.
Pretty much exactly what this guy does. Right?
Okay.
That is pretty much exactly what this guy will do here. So this fellow here will basically be attracted to one of these here. Whichever is most efficient. Why is this the lowest hanging fruit? Because it is closest to it. If there's a large molecule connected here throughout, this is the lowest hanging fruit, right?
Yeah.
So this is your mom or dad's wallet. This is that
Yeah.
tray in the house where there will be a little bit of cash usually kept.
Yeah.
So the lowest hanging fruit is this. So in that lowest hanging fruit, it will pluck the one which is going to be most ideal for it. High value targets, basically. Because it can't go do this many times.
Yeah.
It'll pull whatever is easiest for it to pull, whatever it is most attracted towards. So the attraction depends on the amount of electron density, certainly. But the attraction also depends on how easy it is for this to manage it. For instance, let us say there is $100 bill in your house, US dollar bill, randomly kept for Vastu. Can that be lifted? That cannot be lifted that easily. Because even if you lift it, converting that is going to be a pain in the ass later.
Yeah.
So, coming back to where I was. So the idea here is when you're going to be having a system like this available here, the group which is going to be migrating is going to be density here, but it also depends on R value. Because if the R is smaller, the entire game is changed. Because it's KQ1 Q2 by R squared. So this guy's attraction is definitely more attracted to the R part there compared to the Q. The R part will not matter when there are carbon-carbon bonds. If it's carbon-carbon bond over here, almost always it is going to be only single bond we are talking about here. Yes. Single bond is going to be approximately similar lengths only, not that much difference. That means this carbon, which is in the back fellow here, will be like approximately similar distance from this carbon here.
Yeah.
And it will be similar distance from this bond.
Yes. You can attack any of them.
Exactly. All three of them are going to be relatively equal with respect
equally probably.
So in that case, when it is carbons, the bond electron density factor starts mattering more.
They're also fairly be equal, right?
Yes, that is unfortunately going to be true. But the reality is, this is something which is going to be present closer to this carbon. Correct?
Oh.
Think the bond is what it is attracted to now. That's what it is taking. Bond is a pair of electrons. That is what this guy is attracted.
Yes.
So even if the distance is going to be similar now it doesn't, now it is not about the distance factor truly, but it is definitely going to be having similarities with respect to the amount of electron density, but that is what is going to be more attractive now. Because that is what this guy is going after literally. So in this particular case here, you are going to be having similarities, yes, but there are differences which get magnified at this stage now. So when you're going to be having carbons present over there, the amount of electron density in that bond will start mattering a lot more, and that is what your priority order is based on. That is the priority order here, which talks about this part. That is going to be based on that, same as this part over here. This entire part here is based on the fact that whichever is going to be having more electron density in that particular bond, that is going to be the one which is going to be more strongly attracted by this particular sp2 carbon, which will pull it up. Hydrogen, on the other hand, is purely based on R. Because if it is a carbon hydrogen over here, if it's a hydrogen here, what happens? The hydrogen is extremely tiny.
Yes.
That means this bond, which was carbon-carbon originally like this, is now becoming like this.
Yes.
Which means this guy is now far closer to this bugger.
Yes.
Think of the distance there directly. It's far closer. That wins, hands down. No questions asked.
Okay.
You understand the idea there? There
Yes,
are
sir.
other factors also applicable, obviously, which are going to be involving how much repulsion this carbon over there or that guy is going to. All of those matter. I'm not saying those don't matter, but the truth is, those are going to be there everywhere.
Yeah.
So when you're going to be having those factors, and they are at greater distances as well, much greater distances compared to the electron density in the bond over there. That's why they don't really matter so much. So this is going to be the general rearrangement thingy or rearrangement order for everything. Now,
sir, what if there were two cations attached? Like there's a carbon here, and between there's a normal carbon which is satisfied octet.
Let me ask you a question here. What is the chance of that surviving and you observing it?
Yeah, pretty much 0.
Exactly right.
Yeah.
Then is there ever a chance of that being something which can be studied in detail, even if it exists?
Okay.
You understand where I'm going with your point?
What if there's a plus and a minus?
Think again.
Right.
Think again. Same logic applies. Whether it is a plus or a minus, it is a bullet wound, bro. Think of it like this. How many times do you see a John Wick in real life? Fucking never, right?
Yeah.
Why? Because nobody can survive that many kind of bullet wounds and shit and whatnot. We get shot once, we'll fucking move the fuck away. We'll make sure we protect ourselves like crazy. Right?
Yeah.
That's exactly what happens to atoms and molecules as well. So when you're going to be having an atom or a molecule or a system which is going to be having a charge, any charge, every charged location which is present is a bullet wound for that particular system. It makes it highly unstable. So when it makes it highly unstable, it will, even if there is a possibility of it having a plus and a minus, it will be on different ends of the molecule, different parts or different corners of the molecule, and it will definitely not be on goddamn carbons. It will be on things which can handle the charge in a better manner. Like say a nitrogen with an octet and having a positive charge, ammonium type on one end, and an oxygen with a negative charge on another end. You remember what we talked about in ionic equilibrium? Zwitter ions.
Yes.
That is exactly what you're talking about here. That is the only type.
3 plus.
Yes.
Nothing.
You're saying something now?
No, nothing.
So effectively, those are the only kind of species which actually can manage to maintain two charges opposite simultaneously and stay stable enough to be observed properly by us.
So this shifting only happens for adjacent carbon, right? Or could it happen? I don't think.
Think for a second. Did I
adjacent
tell you anything about what did I explain just now? Did I discuss any conditionalities in chemistry? No. Right? I just discussed the physics of it. Now you use your brain and apply the physics of it with chemistry. Tell me, when will that possibility happen? What did you ask? Ask that same question again.
One second. So I said, if a carbocation is like 2 carbons away from, no, I don't think it would happen. No.
Can it?
No.
What is it dependent on?
Distance.
K Q1 Q2 by R, K Q1 Q2 by R squared. So use your brain. If
Okay.
there is a pipeline available, it can do it. But a pipeline has to be available. And that
What do you
pipeline
mean?
has to be in the first location itself. It has to start at this location itself.
Pipeline meaning like
Start
double.
at this case, wherever we talked about that rearrangement location, it cannot do it. Because electronegativity is a pure distance factor. When you become that desperate, if you become that desperate, you cannot steal from me. You cannot steal from your grandparents so much. You can from your parents. You understand what I'm saying?
Yeah.
But if it is going to be something, if your question, can you technically live from your grandparents? Yes. If it is a passed down item, that can be lifted.
Yeah.
You understand what I mean by a passed down item?
Yes, sir. Yeah.
That is going to be similar to your resonance over here. When there is conjugation extended.
Oh, okay, I see.
From that direction.
Oh, like a okay.
So what do I mean here? Let's say I'm going to be having a carbocation here. Okay. So this carbon is going to be having some bonds over here, correct? So now if the bonds present here, let's say they are like single bonds only, then this will happen. Let's take a double bond on one side. If I have a double bond, what is going to be happening? Which is the lowest hanging? No, exactly. Pi is the lowest hanging fruit. So that pi cloud will directly get pulled here.
Yes.
So if there is a connection for this fellow with another tank of electron density.
So that'll also get pulled.
Exactly.
Oh, I see. Okay. Could you connect that carbon like that? Okay.
Yes. Basically, this fellow's desperation pulls from here, right? Now who becomes
Which
more
causes
desperate?
his desperation.
This guy becomes more desperate.
And that guy pulls that.
This guy pulls it.
Okay.
You understand?
That's universe conjugation.
That is what I was talking about. If you understand the goddamn KQ and Q2 by R squared properly, you don't need to understand anything else.
Okay. Yeah. I understand.
You understand what I'm trying to explain here?
Yes,
Exceptions come into the picture only when your physics is not ingrained. When you link up your chemistry with the physics part bluntly, there are no exceptions. If there are still exceptions, those are very complicated. And you don't need to really give a shit beyond a point here. See, what is the highest stage which a JEE student can reach ideally? Link up all three subjects internally.
Oh, okay.
That is the highest stage a true JEE student, a real top ranker will be reaching. When I say link up, I really mean connect it. Understand the intricate connections here. You can see how there is enough connections in every place. All you have to do is open your eyes to look at it. But they are not easy to look at. It's not like, what to say, others do not see these. It is just that they refuse to look at it. Because it gets very painful to see beyond a point. So in this particular case here, conjugation is literally that only. In conjugation, what is happening here is this guy's desperation makes this guy more desperate, which in turn basically ends up doing the same thing the first guy did, which is attack the lowest hanging fruit. Everywhere, that's the basic principle. K Q1 Q2 by R squared will be followed. Because that's goddamn physics. Physics is not going to be lying to you. So, but at the same time, remember, there are other systems also at play here. You are going to be having other electron densities also present, like nucleuses. Nuclear repulsions also need to be considered. Steric hindrance is predominantly going to be of that factor only. Now, coming back to the elimination bit there, which we were talking about, let's come back to this one. So, HSO3 minus is one pathway, E1 pathway is one. What are the other pathways available? What else can happen? What is this system?
Electron deficient.
Carbocation, electron deficient. So it is an electrophile, obviously.
Electrophile, yes.
And it is attracted to what?
Nucleus. I mean, positive charge.
Attracts electron-rich species, not positive charge.
Oh, sorry, negative charge. Sorry. Yeah.
So it attracts electron-rich species. So if this guy is going to be attracting electron-rich species here, that's why you got your HSO3 minus.
Yes.
That is why we had this pathway, which is pretty much the same thing of what to say rearrangement,
Attracting the bond pair.
Which is what we've been discussing all along. So I'm not going to touch this pathway for now. Let's talk about the third possibility. What else is electron rich? What do I have in the mixture now?
Sir, another molecule of this thing.
Tell me.
Is ethanol.
Wonderful. Good. Not bad. So I will have a molecule of ethanol as well. So you are going to be having this bugger also having
yes.
electron density.
Yeah.
So the problem, the real key problem here is not the HSO3 minus, it is this bugger.
Oh.
Tell me, continue.
This only comes into play when you have excess remaining, right?
So think for a second here, what does excess mean?
It hasn't reacted fully.
No, what does excess mean? Look at it at a molecular level, zoom in and look. How often do you have perfectly homogeneous mixtures formed, dude?
Rarely.
Right? And you have to work at mixing them properly and making them homogeneous, correct?
Yeah.
So if I have a beaker which is going to be containing some ethanol and I add some sulfuric acid concentrate to it and I start heating it, that's pretty much what I'm doing over here, right? In that case, there are going to be pockets of that mixture where ethanol is going to be in much larger quantity there, correct? In those pockets, technically it is in larger quantity, right?
But then why are we assuming that it's not uniform?
I am not assuming it is not uniform. I am trying to see what are the possibilities.
Oh, okay, fine.
Which are meaningfully capable over here to happen.
But that also means assuming that it's not uniform, right?
No.
If it was perfectly uniform, then nothing.
I will have to study when it can form and when it will not form. Because I am not supposed to be, see, what are we trying to do here? We are trying to analyze what are the various possibilities to understand truly when we will be getting what we will be getting. Say, for instance, if I'm going to be looking at you, you're a student. You have many possible options in front of you right now. As you grow older, the number of options in front of you will keep increasing. Right? But when you are smaller, your options are much more limited. Correct. So this is basically a type of scenario where you're going to be having many options available. And the more limited the options are, you have to be careful to see what are the limits in that options there. Let's have a look here. This ethanol here, if it does attack, there are some requirements for it to basically attack that. It should not be dominated by the sulfuric acid completely.
Correct.
Right? That is absolutely a first requirement. That means if I have like tremendously large amount of sulfuric acid and a tiny amount of ethanol, this is going to be much more lesser in quantity. Fair? Yeah. But if I have only a small amount of corn sulfuric acid added and I have a tremendously large amount of ethanol available anyway, then in that case, this becomes a far more easier possibility to see. Right? Enough ethanol molecules will be around. What will happen if an ethanol molecule attacks?
Then this lone pair will go there. Yeah.
And the hydrogen will get kicked out.
Yes.
So I will be left with this.
So why?
I will get this guy first.
Yeah.
I'll kick this bugger out.
Oh, sorry. Yes. Yeah.
Right? Which will result in what?
Ether.
Yes. This is called as an SN1 pathway.
Oh, SN1, SN2.
Now, When we are talking about this pathway here, let's try to observe each pathways properly here. First of all, this is the worst. Why is this the worst pathway? Because this is going to be the worst base.
Oh yeah, correct. Yes.
Nucleophile among the bunch available here. Because now you need to start checking which fellow will donate nicely.
Basically,
You want to start looking at the different paths here. The way you observe the different paths has to be, what are the hindrances for each path? What is the thing which is happening?
extent of donating.
So in this case here, the idea here is this is going to be your worst fellow here. So this path is the worst here. So this will give you unnecessary product. I don't need to care about it. The E1 pathway looks nice, but that is actually a far more complicated pathway. Look at the scenario here. If I'm looking at the energy profile diagram, I have seen that your energy profile diagram in many places there. So that means you should have a reasonable idea as to what an energy profile diagram is supposed to be by now. So let's start talking about the energy profile diagram. I'm going to be having reaction time.
Progressive.
Or any scale of time. As I wish. It doesn't have to be time really. And here I'll have energy. So in this here, how is this going to look like here? So let's say I'm starting off with
C2H.
Alcohol. I'm going to start off with alcohol, ethanol here. Okay. So I start off with C2H5OH at this level.
Stable.
Okay. Now, what happens first? This guy effectively ends up becoming the OH2 plus.
So very high energy.
So OH2 plus. Then what happens to the OH2 plus?
Sir, why is it at the dip?
That becomes a carbocation.
Sir, why is the OH2 at the dip? It should be at the...
Fine. The dip is going to be something which is going to be mainly present because you're going to be having at the instant when the bond is being formed, you will have the species being a little bit less stable. Think for a second what is happening. Why did I put it at a dip? What is that first step actually? If you want to understand why it's a dip, think about what is that first step. Closely.
Becoming... One second. What's happening? H plus. Oh, first the H plus in the solution.
What is that first step? Think now.
Dissociation.
Think.
H2SO4 dissociation. It's a strong word.
So tell me now, if H2SO4 dissociation is going to be happening, when will it happen?
When there is a base.
Who is the base here?
This C12OH.
So now you tell me, what is that stage? What is that?
Oh, neutralization.
Not neutralization. That top part there where it is going up now, that is when it is in that stage like this. That up part is literally going to be, this part over here is literally going to be that instant where the acid and the base are about to react, but they have not reacted. Basically, the hydrogen has broken off, but it has not yet combined with the base here.
Not yet combined with the base. Yes.
Just that instant. Think what happens. I have H2SO4. Basically,
I understood. Okay.
This guy, correct? This instant where this fellow is supposed to combine with my OH.
Yes.
It's supposed to happen in instantaneous fashion. But nothing is instantaneous really in life, right? So, the instant when this breakage is happening, that is this part. The uncombined H plus then combines with the OH and it ends up coming here. So you can think of this level here as a mixture of C2H5OH, H plus and HSO4 minus. All together in the same, at that same instant.
Okay.
Then you end up having this guy becoming C2H5 OH2 plus.
And HSO4 minus.
You understand what's happened there?
Yes, sir. Yeah.
So effectively, you're going to be having, what to say, you have to be careful about how you draw things. Every bit of it, unfortunately, has something attached to it. Not bad, good question. Okay, now next what will happen?
Then
will
we remove the water.
Plus,
yeah,
right?
Remove the water.
It will go up to a much higher spot. Say here. This is going to make carbocation now. Correct? After that carbocation is formed, what will be happening? It has a few now in its it has a few paths it can take now, correct?
Yeah, different colors. Okay.
One second. I want to know how to cut this out. Oh,
adding H2O, sorry, removing H2O requires an okay.
That's why it's going up, na?
Yeah, understood. Yeah.
Now, next step, what will happen here? Next step. Now it has
three. See the HSO4, HSO3 minus.
We eliminated the HSO3 minus nonsense, correct?
Oh,
so let us. It's a nonsense pathway, right? That's not going to be giving you that much result there. Why? Because that guy also has its own activation there to give it.
So even going high,
tougher. You're understanding the point now. That will go high. Even if this is going to be after it goes up, it will come down greater. But it goes up too much, na? So done.
Yes.
No chance of it ever happening.
Correct.
So now let's look at the other two pathways here, E1 and the alcohol one. Now in the E1 pathway, what is happening? A bond is being broken directly.
Breaking and making also.
The making is happening, but the bond is being broken.
Yeah, endothermic.
Think for no, it doesn't matter. Don't stop thinking about that nonsense. Stop thinking exo-endo nonsense. Stop that for a second. You are not in that mode right now. That comes after you have done your this thing. So close your brain to that filter now of endo and exo. What is happening now if I'm doing an E1? If I do an E1, it is going down a pathway where it is having a high activation energy because it has to break a bond. It then ends up becoming a more stable system.
Right? Makes sense. Yeah.
Right? So it will go like this.
It's now,
unhappy with the previous stage because I put it above this. That is wrong. What is the product formed here? Alkene, correct?
Yeah.
The ene is going to be lesser than the alcohol in stability, but definitely far more than the OH2 plus.
Positive charge, obviously. Yeah.
So why is it lesser than the alcohol though?
1 second. There's a pi bond, so there is a
good. Pi bond is less stable, as simple as that. Sigma bonds are more stable. Why? Because they are attracted more strongly. Stability depends on level now.
When we're comparing structures, we say that more number of pi bonds more stable, right? But here it's not the same. Okay, wait. It's not the same species kind of thing. That's an alcohol. This is okay.
There are substantial differences.
Yeah. Yes.
One is an alcohol of same number of carbons. One is the alkene of the same number of carbons.
Can't really compare that. Okay.
So this is going to be the E1 pathway. You understand why this peak is so much higher?
Yes. So can you explain how the double bond is formed once?
We'll talk about that in a bit when we get there. Let's first understand the problems over here. Then we'll get to the double bond formation. That's going to be much longer topic.
My class will start in like 5 minutes.
What the fuck? It's at 9:30 now?
Yeah, it's at 9:10 apparently. They changed the time.
Okay. All right. Okay.
Sir, can you take another class in the evening if possible? Or anytime?
See, I am going to the zoo with my daughter today, bro. I'll come back late in the evening. I have no problem taking a class. But it will be like say 7:38 ke baad.
That's fine with me, sir.
Raat mein.
Yeah.
That's cool with you?
Yes, sir.
Then we'll join up again then.
Okay.
So in this here, we'll finish up first this shit
Yeah.
here.
Yes.
So this E1 pathway here, I want to basically make sure you understand why this point is this high. Why is this point this high first?
1 second. Because we need to break the bond.
You need to break a bond.
Yeah.
So when you're breaking a bond, there is going to be that instant stage where the bond has broken, but the guy has not been combined yet.
Mhm.
So that is going to be the pressure point, the pain point over there. So that is going to be the reason for that. If you look at the SN1 pathway though, what do you think that will look like?
Wait. So it's bond making again.
Mm. And is there
So-
any bond breaking thingy happening there?
No.
That means the
Wait,
activation
afterwards,
is
yes.
very easy there, correct?
A little lesser than this.
Not just lesser, it will look like this bluntly. That is, if I'm changing for this new pathway here, it will basically be like this.
That's
उस type का होगा.
sir, but will it be more stable than alkene? The ether?
You think for a second and you tell me. The first stage will get the O plus. Then the O plus will effectively end up becoming an ether, correct?
Hmm.
What is there in the ether? Only sigma bonds.
Hmm.
So where will
Harder
it
to
be?
break. Okay.
You understand what I've drawn here and why I've drawn it like that?
Yes, sir. Understood.
This O plus is supposed to be on roughly similar levels as this. This ether is supposed to be on roughly similar levels as this guy.
Sir, why is the O plus supposed to be the most?
Think.
Isn't there also an HSO4 minus?
My dear kid, what did I mention here? I said O plus and I pointed to this. I didn't point to this.
No, but when you're when the H plus reacts with OH there, the HSO4 minus is still there, right, in the solution.
Yeah.
So it should be there in that dip as well, right?
How are they behaving here in this part here? Are they taking part over here in this point here? When
No.
the O plus is formed, how is this O plus formed?
So that HSO4 minus is still in the solution.
Wait, I'm talking about this step, da.
Huh.
Where is the HSO4 minus here?
No, I'm talking about in the first case I'm saying.
That is going to be there from beginning.
Initially.
So
okay, that's my doubt. It will be there in the
you're
solution.
asking what happens with the HSO4 minus path?
Yes.
That path will not be something which is this nice. That path will look like this.
This is only drawing for the C2H5OH.
Yes. I am only drawing for the other two more easier paths.
Okay.
The HSO4 minus path will look like this.
Sir, we can't just remove it from the solution, right?
I am not removing it. I am not considering it. That's all.
But we can't remove it, right? If we want
can't.
it also.
We cannot. How can we remove it?
Yeah.
We simply cannot. Can I remove all the salt from your body? What nonsensical question is that? You cannot, right?
Yeah, yes. That's right.
Same thing.
Okay.
So effectively, the HSO4 minus path will look like this. This extremely weird path here, which goes up over there. I have not even put down the ending because I have to think where the ending will go. And I don't want to commit to something randomly. So idea here is you're going to be having the pathway being very high in terms of activation energy. Why? Because there something which is not normally going to be giving away electrons is giving away electrons. Right? That gauge is already much more stable. So the path for that is going to be higher.
Okay.
And if the path is going to be more tougher, less walked on.
Okay.
The probability of that happening decreases dramatically. So here in this particular case here, this is basically going to be your three paths here. Among these three paths here, as you can clearly see, the SN1 pathway is actually
stable. Best way to.
Yes. That is the easiest to do. So you've done Le Chatelier's principle, correct?
Yes, sir.
This is where there are two ways of looking at it. In this case here, there are two pathways which are competing here, SN1 and E1. You need to understand which one is going to be doing what at what time, under what conditions. If you understand that part more clearly, you don't need to remember things for E1 more properly. Then let's quickly think about what are the basics over here. So SN1 there is lesser activation energy. You understand activation energy or not?
Yes, sir. Yes.
So there is lesser activation energy. And in terms of what to say, exothermic, endothermic. Now tell me the SN1, what is that approximately going to be?
It will be endothermic.
No, it will be nearly neither.
But like it's oh yes, sorry. Correct.
Nearly neither.
Hmm.
Not perfectly neither. That would not be perfectly correct as well, but close to being neither. Why? Because they are at similar energy levels.
Yeah, yes.
Right. Whereas E1 on the other hand, this is going to be
Endothermic.
endo. Now, these are your two pieces of data here. So endo, I'll put it at the bottom there. Higher react is the more important one here. And endo. Now, these two are going to be deciding the temperature conditions and other conditions when E1 will happen better. When you did this corn sulfuric acid, concentrate phosphoric acid, I mentioned heating over there, correct?
Hmm.
That
Oh,
heating
yeah.
is to get a little bit more of the E1 product.
Energy. Oh,
It is to get a little bit more of the E1 product, which is competing with the SN1 product. You will get the SN1 product to be more predominant if you are having lower temperatures.
lower temperatures. Lesser activation energy. Okay.
नॉर्मल रूम टेम्परेचर के आसपास है तो E1 के बदले में SN1 आ जाएगा. So that is basically the key thing, because you will see the same stupid reactions again in the other chapter.
Okay.
And when you see them there, it will be like, oh, why this place this way, why this place that way. So I suppose I'll shut up now. Your class should be starting soon.
Yeah, it's
So started already.
Yeah, I think so.
Bye bye.
Yeah, thank you, sir. Have a nice day.
We will see again. We'll meet
Yes, sir.
each other again. See you.
Yeah. Okay.